Okay, so the last thing we have to look at for the organic chapter is the properties and reactions involving benzene. So benzene is classified under a group of what we call the aromatic hydrocarbons. Okay, the name originally came due to the smell of these things containing benzene. They have a very distinct aroma to them, hence aromatic. Um, we now know that a large number of these compounds, though, are highly toxic, highly cancerous, so they're not something you really want to be smelling. These aromatic hydrocarbons, the key feature is they contain the phenyl functional group, or a phenyl or benzyl, aka benzene ring. And you can see the structure below. It is in resonance, so it's a six-membered carbon ring, okay, with one hydrogen attached to each carbon, and it has those repeating double bonds. We see the resonance structure here where the double bonds alternate back and forth. Okay, now this structure was originally proposed by the chemist Friedrich August Kekulé, okay, the alternating double bond structure seen. He had a dream about it where a snake was eating its own tail, and he claims that this is what brought him to the conclusion of the structure of benzene being the ring like this with this alternating bond structure. Okay, and this structure was used for years until a lot of evidence started amounting showing that it doesn't quite fit the properties of benzene correctly. So first we're going to take a look at these few pieces of evidence and then jump into the reactions involved in that benzene is involved in. So what does benzene actually look like? So the first piece of evidence that goes against this alternating double single bond structure, okay, is the carbon bond length. The reason being, so the carbon bond length in a single bond, right, is 154, and in a double bond is 134. So if we had our benzene structure with our alternating double single bond rings, we would see these single bonds, right, would be 154 picometers, and the double bonds would all be 134 picometers. And as it alternated, we would be able to detect this, and the bonds would be constantly shrinking and growing in length, causing benzene in kind of like a fluctuation. But it's not. So when benzene was studied, it was found that all six of the carbon-carbon bonds present were all equal in length at 140 picometers. Can you'll notice that that is in between the single and the double bond. So each one is kind of halfway between single and double. In fact, we would say that it has a bond order of a 1.5 bond. The second piece of evidence is the isomers and reactions that benzene undergoes. So when you substitute benzene with chlorine, for example, as seen here, we have two isomers of chlorine. The first one here where we have the two chlorines on either side of a double bond, and the second isomer where the two chlorines are on either side of the single bond. Right, so these two isomers would have different properties. They would be able to be substituted differently in other places depending on what reactions we were doing. But it was noticed that although seemingly there's two, there in fact was only one. You could not get two different isomers of 1,2-dichlorobenzene. Only one existed. And the second piece of evidence is that if you remember from our lesson in alkenes, if we added to benzene, for example, a bromine, okay, we should be able to get the addition of bromine across either side here. So remember the double bond would break, and we would get the addition of bromine, and okay, it's an alkene, that makes sense. But benzene does not undergo addition reactions. Okay, so that was another piece of evidence, because if it had this single double bond structure, we'd be able to add things to it quite easily, but we can't. Okay, so it does not undergo addition reactions. And one of the reasons is because of this resonance, it keeps it what we call resonance stabilized. We'll talk about that in a little bit more later. So the third piece of evidence is the bond enthalpy. Okay, so if we take a look at cyclohexene, we hydrogenate Okay, we do the hydrogenation reaction, so we add an H2 across the double bond here to make cyclohexane. And we find out that adding an H2 across the double bond has an enthalpy of negative 120 kilojoules per mole. Benzene, having 3 double bonds, if we add 3 H2s, should have an enthalpy of 3 times the amount of cyclohexene. But what we actually find is it's not 3 times the amount, which the theoretical would be, but it is in fact only 208, okay, instead of the 360 that would be expected. So it's quite a bit lower. We don't get quite as much energy out when we perform the hydrogenation. Okay, and the reason again behind that is because benzene has this resonance where it's sharing all of the double bonds, it is quite stable. So these 3 pieces of evidence led to scientists and chemists, researchers, to devising a new idea of what the benzene molecule looked like, slightly different from Kekulé's original benzene structure. So this new benzene, the actual structure, we still have a planar molecule. Okay, so its benzene is flat. Its bond lengths are 140, bond angle is 120, and the electrons in benzene are delocalized. Okay, so they don't hold their place in these double bonds and then switch back and forth from one spot to another. It's actually that the electrons are completely shared. Okay, so we call it a pi electron cloud. We get in a little bit more into pi electrons in chapter 14. So the electrons are delocalized, being equally shared evenly amongst the 6 carbons. So this is why all the bond lengths are even, and this even sharing is what actually stabilizes benzene and makes it not undergo things like addition reactions. Okay, so the electron density exists in rings above and below the planes of the molecule. So that's where we would find the sharing of all of these electrons in those rings you see in the image. And benzene is often represented with a circle to represent that delocalization of electrons. So some reactions with benzene. Benzene, number 1, does not undergo addition reactions. So an addition reaction would break the double bond, disrupting the resonance. So if we had, let's draw Kekulé's version of benzene down here, which we'll often draw when doing reactions. If we were to add, let's say, we'll go with a bromine here, across one of the double bonds. So we have bromine, and we would still have our other double bonds here. Now what's happened is we've removed, so here we have the continuous sharing of these double bond. So we have this continuous pi cloud, or the cloud of electrons that's shared amongst all the carbons. Here what we've done is we've broken it. So now we've added bromine, so there would still be our hydrogens on these carbons as well. Okay, and benzene of course has 1 hydrogen on each of its other carbons. Okay, we can no longer have this complete sharing. So we've destroyed the resonance. We've destroyed this continuous pi cloud. It's only on half of the molecule now, which really destabilizes benzene, putting it into a higher energy state. And we don't want that, right? So resonance is quite important. Keeping the resonance keeps a benzene stable, so it won't undergo addition reactions. But it will undergo substitution reactions. So we can replace a hydrogen on benzene with another different atom, and it does not break the resonance because we're switching one thing for another. We call these reactions electrophilic aromatic substitution reactions. Okay, so let's break it down. What is an electrophile? So remember, a nucleophile from before is something attracted to positive charges. Well, an electrophile is something attracted to negative charges. Okay, so it's attracted to electrons, in other words. Now, benzene, having these rings of electrons, right, has a buildup of negative charge in one area, so it's quite attractive to electrophiles. Aromatic, because we're dealing with benzene, which we call the aromatic hydrocarbon, and substitution, because we're replacing one thing for another. Okay, so it does require, when you do this, the resonance to break very temporarily. So we do need quite a strong electrophile in order to react with benzene. And the first one that'll work is the nitronium ion. Okay, this is a longer reaction we'll look at later in chapter 20. For right now, you just know that you can form the nitronium ion from benzene. So we take benzene, we add nitric acid with a concentrated sulfuric acid catalyst, heat it up a little bit, and what this does is it forms nitrobenzene by adding the NO2 to our benzene ring. The second reaction is we can use halogens to form an aryl halide. So aryl halide being an arene or a benzene ring with a halogen substituted on it. So we take our chlorine, okay, and we have to use a AlCl3, so an aluminum chloride catalyst, in dry ether. So ether just being a solvent in this case. Dry means without water. Okay, so we take our chlorine, our benzene, and we can get chlorobenzene. Okay, if we were to use, for example, bromine in this reaction, then we would have to use aluminum bromide in order for our catalyst in order to brominate the benzene instead of chlorine. So the catalyst does change depending on what you're trying to add. Okay, so these are two examples of electrophiles. Again, our halogen and our nitronium ion, two different things we can do to attach or substitute something onto a benzene ring. That brings us to the end of benzene and the end of the organic chapter.